So there's a magnetic field around every wire, and just going to see how that compares to the magnetic field that you would get, for instance, with a bar magnet. That's a permanent bar magnet. You've got the north to south, just like we saw with the magnetic field around the Earth. That would be a permanent magnet. If you have a single wire with a current flowing through this is a bit of card, and that's the wire going up and down into the card, and this is the surface of the card. The iron filings demonstrate that there's a circular magnetic field. The shape of the magnetic field and the directions are shown by a left-hand grip rule. Now, you will see different rules because most of the rest of the world uses conventional current flow, where conventional current is positive. All these slides assume electron current flow. So your thumb is the motion of the electron current, your fingers wrap around in the field of the circular magnetic field, and that's how you can tell the direction of the field that you get in a wire. Obviously, flip the wire upside down and the field lines would wrap around the other way. Calculations are based on this equation here, where you're given this in the formula sheets, that magnetic field B at any point out radius r from a current is mu naught I over 2 pi r. Right, mu naught is a constant, the permeability of free space. It's basically how good a vacuum can be at holding magnetic fields. Other different materials, such as soft iron, are much better at holding magnetic fields, and therefore they have a higher permeability. Quite unusually, there's pi involved in this constant. It's because it cancels with the pi underneath there. Just don't ask at the moment. But you have a constant, just to keep the units right, which is 4 times pi times 10 to the minus 7 henries per meter. Again, that's given on the SQA's data sheet, but that's the formula, and that's the constant that you use. So all your units are ampere for current. Induction, magnetic induction is often how it's referred to in the exam paper rather than magnetic field, and your distance has to be in meters. The nice thing about this is that it's an inverse relationship because it's over 2 pi r, and you get an indication of why it's over r because it's the circumference of the circles as they go further out. Really, the magnetic field is having to be distributed over a greater circumference rather than inverse square, where it be distributed over a much wider sphere. So you should be able to appreciate that if you plotted the magnetic field at different distances, you would end up with inverse graph like that. And if you wanted to get a straight line graph from that, you'd have to plot b against 1 over r to give you a straight line, but I'm sure you know that by now. So try this calculation. If you had a kettle with 13 amps of mains current, we're going to assume that there's not the neutral current coming in the opposite direction, which actually cancels out this effect, but just humour me with this one, that we've got 13 amps of current, and you put something 3 centimeters away from it. How much magnetic field would you get? So pause this for a moment. Firstly, put in the notes and the worked example, then try it yourself. Okay, so you've hopefully got your own answer for that now. So let's see, you should have mu naught I over r, that's your numbers, that's the current, that's the distance, and that should be your answer. You may remember in first year that you did an experiment with a big nail. You certainly did this in third year as well. And you wrapped lots of turns of wire around it, and it picked up metal things because you were made a metal electromagnet. So this arrangement is called a solenoid, and all we're doing here is actually taking that magnetic field around a wire, and because we've got so many wires all with their own magnetic field, the magnetic fields add together and gives you this effect where you can actually get a much stronger magnetic field rather than the weak magnetic field due to one wire. It's not part of advanced hire, it used to be, but it's just to show you how this would be used, and there's a short video at the end that just takes you through how solenoids are actually used and how the solenoid builds up from the single wire magnetic field. So just to recap, SQA say you would be able to use an appropriate relationship to solve problems involving magnetic induction around a current carrying wire and the current involving the current and the distance from the wire. So that's the one.